All right, Algebra 1A students, welcome to part 2 of your video on lesson 6.2, solving systems by substitution. Again, just like our last video on lesson 6.2, we are solving systems, again, algebraically, systems of two linear equations, solving them algebraically, trying to find the solution. However, there are certain situations when we're trying to solve a system of equations where we don't get just one answer, we get something that isn't supposed to happen. It's sort of like when we were talking about graphing systems of equations. In our last video, I showed you an example where you have two parallel lines that are never ever going to cross, and they just keep going at that same kind of slope, and they're never going to cross. There won't be any solution. There won't be a point where those two lines intersect. So we can end up with things like that when we're solving algebraically as well. Now, sometimes we can find a solution, a system of equations that has what's called infinitely many solutions. Another way to say this that I prefer is just to say all solutions. Means every number you could possibly think of would be a solution, so that is the same as all solutions. I don't care which one you use. We can also end up in situations where we have no solution. Okay, so what we're going to look at in this video are a couple examples of systems of equations that have all solutions or infinitely many solutions, or they have no solutions. Okay. So if we look at each of these systems, I'm going to solve them again with substitution, as I did in the last video. First of all, I'm going to notice here that my x variable is all by itself. I know what x is equal to. It equals negative 2y plus 4. So instead of in my second equation putting an x, I'm not going to write x. I'm going to write negative 2y plus 4. So my second equation now is going to say 3.5 times in parentheses negative 2y plus 4. It's very important to put that in parentheses because I'm going to use the distributive property here in a second. Plus this 7y that still exists is equal to 14. Now I want you to notice that this is a rather complicated looking equation, but the good news is it only has one variable. So this is something that I can most definitely solve for y and try to find that. So what I'm going to do is do the distributive property and see what happens. When I do 3.5 times a negative 2, I get negative 7, and that has a y on it. Okay. Plus 3.5 times 4, which ends up being 14. And then it says plus 7y equals 14. Okay, and now I can combine the like terms that are on this left side. I see a negative 7y here and a plus 7y here. I'm going to add those together. When I add a negative 7y plus 7y, how many y's do I have now? I have none. I have 0y. So that's like it doesn't even exist. 0 y's do not exist. They're not there. They've disappeared. They've gone away. Okay? And when everything, when all of my variables go away, in this case my y's cancel each other out and I don't have any y's left, what's left in my equation? Well, all I have is a 14 on the left side because this is gone and this is gone. And then I have a 14 on the right side of the equation. Okay? And now this is kind of what I get for my answer. I just have 14 equals 14, and you might ask yourself, well, what are you supposed to do with that? There's no variable that I can solve for anymore. So once all of my variables disappear, I now am left with two options. It's either no solutions or it's all solutions. Okay? And I figure that out by just looking at what's left. Okay? If I am given something that is true, if I'm left with something that's a true statement, like 14 equals 14, that is true. It certainly does. 14 is the same as 14. That's true, which means I have a system with all solutions. Every number that exists in the world is a solution to this system of equations. So I have all solutions, and I don't have to go any further. all solutions. Now, if I look at this other example over here, letter B, if I go through the same process of noticing that my y variable here is all alone, so I can replace this y variable with everything that it's equal to in the first equation. Instead of writing y minus 3x, I can write 3x minus 11 minus another 3x equals negative 13. And now I want you to notice that exactly the same thing is about to happen. I'm going to combine the like terms on the left side of my equal sign. That's this and this. That says 3x minus 3x. 3x minus 3x. It's a 3x and it's a negative 3x. When I add those together, when I put them together, when I combine those like terms, they disappear. 3x, take away 3x, is 0x. And 0x is like it doesn't even exist. There's no point in even putting it there. This 3x cancels out with this minus 3x, and it's just gone. So what's left then in my equation? Well, what's left is negative 11 equals negative 13. Because the only thing left on the left side of my equal sign is a negative 11. The only thing on the right side is a negative 13. Right? So, in this case, I have to look again at what is left. Look at what's left now. Well, what's left is negative 11 equals negative 13. And the question that we need to ask ourselves is, does negative 11 equal negative 13? No. That is absolutely false. It's not true. Negative 11 does not equal negative 13. When I'm left with something that is false, I have no solutions to this system of equations. There are no numbers that make this system of equations true. It is impossible to make this true. Okay? So when you end up with something that's true when all your variables disappear, then you have all solutions. When you end up with something that's false, you have no solutions. Okay? If you have questions about when we're going to either have no solutions or all solutions, because it doesn't happen all the time, just rarely does it happen. If you have questions about when it happens or what to look for when it's going to happen, please make a note to ask me in class tomorrow. Otherwise, that's all I have for you. Have a wonderful night.